So you are more than welcome to do corrections. I would like them by next Friday. But again, if you just, assuming you can go into the grade book, and on the test, there should be an icon that you can click to see comments. So if you missed anything, it would be written in the comments. Email corrections to me, and I will put them in the grade book. All right, we've got two really short lessons today. So if you looked at Tuesday's lesson, we took a function or a graph, and we estimated the area between the graph and the x-axis. And there's a good reason we did that, that you will find out here in a few days. So that took care of the areas part of 5.1. Today we're going to talk about the distances part of 5.1. So distance, similar to area, can be found using a very simple formula, one that you've probably used maybe a time or two. Distance equals rate times time. If velocity varies, then it's not as easy to calculate distance traveled. The distance equals rate times time is based on an average rate rather than a continuous rate. So in our previous algebra, you would be told, oh, someone travels at an average rate of 50 miles an hour and they travel for 4 hours. How far did they travel? Well, with calculus, we can be a little more accurate. We don't have to talk about average rates. We can talk about rates that change. Hey, Grace. So suppose the odometer on your car is broken, and we want to estimate the distance traveled over a 30-second time interval. So we look at the speedometer and we record the following readings on our speedometer. So every 5 seconds we look and we jot down what the speedometer reading is. By the way, don't do this if you're driving. You know, that's not very safe. So we can use this information to calculate distance, except for one problem. Can anyone spot the problem? Give you a hint. Time is in seconds and velocity is measured in miles per hour. So we do have a units issue, but we can take care of that. So in order to get velocity and time in consistent units, we could either convert our seconds into hours, which I wouldn't recommend, or we could convert our velocity, and a good way to convert that would be into feet per second. And so 1 mile per hour is 5,280 over 3,600 feet per second. So if we take each of those velocity measurements and multiply by 5280 and divide by 3,600, we get the following data, which is now in feet per second. Excuse me. All right. In this case, our velocity is pretty consistent, right? It doesn't change a whole lot over any time interval. So we are going to do one little assumption, and the assumption is we're going to assume that it's changing at a constant rate. So what we're going to do, similar to our area approximations with distance, we can make a right-hand approximation or a left-hand approximation. So for our left-hand approximation, and I'm going to go back to the table just for a second. Our delta x in this case would be our change in time. It's 5-second intervals. Left-hand approximations, we would go with 25, 31, 35, 43, 47, and 46 for our velocities. For a right-hand approximation, we would take 31, 35, 43, 47, 46, and 41. So because that time interval is the same for each velocity, I can factor out that time interval of 5 and add my velocities. And what I would get is 5 times 227, which is 1,135 feet. And if you don't trust me, you can, feel free to double check my work. I know I would. So that's our left-hand approximation. We could also do a right-hand approximation. And again, just like with functions and graphs, the only difference the first value in our left-hand approximation does not occur in our right-hand approximation. And the last value in our right-hand approximation does not occur in our left-hand approximation. So you can see, I think, that there is a 16 feet per second difference in the left and right-hand approximations, that 41 minus 25. So 5 times 16 is 80. So I should have about 80 more feet if I did that correctly in my head. Oh, look at that, 80 more feet. So again, our left-hand approximation, we traveled about 1,135 feet. Our right-hand approximation, about 1,215 feet in that 30-second time period. So with our distances, we use the exact same format as we did with when we calculated the area with our rectangles. So one interpretation is that the total distance traveled can be thought of as the area underneath the velocity curve. Take and graph out velocity, estimate the area underneath. That's our total distance traveled. Pretty neat. I know you're all impressed. You don't have to pretend. So as I said, we have two really short lessons. So that's the end of the first lesson. So your assignment will be on 341, 342, numbers 11 through 15, and number 17. I am going
Do you think you could flip back to that last slide for just a second?
Absolutely not. Oh, absolutely. That's what I meant. Absolutely. There we go.
Thank you.
You are welcome. I am only here to serve. All right. So I'm going to save that quickly. And then we'll do the next one. Maybe I'll save it quickly. All right. Oh, there are your answers. All right. So 5.2 starts our talk about this thing called a definite integral. And as I said on Tuesday, the integral is like the second half of calculus, with the derivative being the first half. So I am going to minimize. There we go. If we have a function that is continuous and defined on the interval from a to b, and we divide that interval into n subintervals of equal width, just like what we did on Tuesday. You take the interval of the graph, you divide it into equal subintervals by taking the upper limit minus the lower, the upper value minus the lower value, and divide by the number of subintervals we want. And then we let x sub 0 all the way up to x sub n be the endpoints of those subintervals. And then we choose some sample points. And let me just kind of describe what I'm saying here. So we're going to pick x star sub 1 to be some value between x sub 0 and x sub 1. So if we were doing left-hand approximations, x star 1 would be x sub 0. If we were doing right-hand approximations, x star 1 would be x sub 1. And so all it's saying is x star sub I lies in the ith subinterval. It is somewhere between x sub I minus 1 and x sub I. Then we define the definite integral of that function from a to b. So here's the notation. So let's take the integral from a to b of f of x dx. That's the same as taking the limit as n approaches infinity of I going from 1 to n of f of x star sub I times delta x. Again, that should be somewhat familiar from Tuesday. This integral symbol was introduced by Leibniz, and it's just called the integral sign. The notation, the integral from a to b of f of x dx. F of x is called the integrand. The a and the b are called the limits of integration. The dx really has no meaning. It just tells us that when we take the integral, we're taking it with respect to x. So it tells us kind of the variable that we're interested in. Now, in single variable calculus, there's only going to be one variable there anyway. Some people like to kind of equate the delta x and the dx as the same thing. Not really, but it's one way to think about it. Whoops. Try to go one at a time here. The definite integral is a value, and it doesn't depend upon our variable. So we could have a function written in terms of r, like we could take the integral of pi r squared dr, and that would give us a value that has a specific meaning. It could be x equals a function of y, and then we have the integral of f of y dy. That's okay. All right. We're assuming f to be continuous. So that limit as n goes to infinity will always exist. And as we talked about on Tuesday, it doesn't matter where we pick the sample points in the subinterval. We could use left hand, right hand, midpoint, somewhere in between those, as long as we are consistent in where we choose our value on each subinterval. That sum is called a Riemann sum, after the German mathematician Bernhard Riemann. If our function f is positive, then the Riemann sum can be interpreted as the sum of the areas of the rectangles that we talked about on Tuesday. If f takes on both positive and negative values, because we're thinking of that in terms of area we always talk about as being positive. So the sum would be the difference between the area above the x-axis and the area below the x-axis. Normally, if we're using rectangles to approximate that, and the height of our rectangle is our function value, that difference, the negative area, so to speak, is taken care of because f of x would be a negative value. So normally we don't have to really worry about it unless we were just told, hey, here's some values, find the sum. And then we'd have to be careful on what is above and what is below the x-axis. All right, so we're going to do some, it's always fun stuff because it's math, but we're going to take an expression for a sum and rewrite it as an integral. So we want to rewrite the limit as n approaches infinity of I going from 1 to n of x sub I cubed plus x sub I sine x sub I all times delta x. And so I'm going to help you out. It's going to start with an integral symbol. That is a very bad integral symbol, though. See if we can do better. There we go. The endpoints of our integral become our limits, and it's always left hand or lower value on the bottom, right hand or upper value on the top. I shouldn't say always. Most of the time it's written that way. There are times when it's different. Now, the technically difficult part here is writing our integrand. All of these x sub i's change to just x's. And we should, just to be very specific, put that in parentheses because we're taking the integral of that whole function. And our delta x becomes a dx. That is the way we would write the expression for the given sum as an integral. Yay, we can write integrals now. So your assignment, you're going to be doing some of what was on Tuesday's assignment, finding the area or estimating the area under a curve using left hand, right hand, and midpoint approximations, and then writing a sum as an integral. So a little bit of review from what we did Tuesday, a little bit of just the writing and using the notation for an integral from today. Questions? All right. So again, if you want to do test corrections, they should be available. If you go to your grade in the class, just check the comments for what points were taken off, and email those to me by next Friday. So I'll give you a week. Otherwise, have a great weekend, and I'll see you back next Friday.